This will be our last lesson of the year. We're going to talk about electrolytic cells. We've been talking about voltaic cells, and as we reviewed in the do now, you know with voltaic or galvanic cells, E cell will be positive, and you will have a thermodynamically favorable reaction with the negative delta G. We're going to talk about electrolytic cells today, and these are going to use electrical energy to generate chemical change. These are thermodynamically unfavorable reactions with negative E cells. And you'll see that a power source must be supplied in an electrolytic cell, and that's what you're going to see right here. We'll walk through several examples. A lot of what we talk about in electrolytic cells is quantitative, and it can be without a calculator, so we'll just review some key strategies to get that done with minimal stress. With electrolysis, as I indicated, you're going to have a thermodynamically unfavorable reaction. So if you look at this electrolytic cell shown here where you're electroplating a spoon, let's say you want a silver spoon for example, you have an anode right here which is silver, generating silver ion with the loss of an electron. The electrons again travel from the anode to the cathode, nothing different there in terms of what you saw with galvanic in regard to electron flow from the anode to the cathode. But a key difference is right here because you must have a power source. It can be a battery, some type of power source that will drive the reaction since it is thermodynamically unfavorable. The electron will be gained by the silver ion in solution to generate silver, and you'll plate that spoon. You'll generate a silver spoon. There are many, many practical applications for electrolytic cells. You can charge a battery, generating aluminum, especially if it's depleted. Also chrome, silver, gold plating, any type. And I'm just trying to think. With certain rings that are white gold over time, they will yellow and you will rhodium plate a ring, and that's the same type of process.
For a lithium-ion battery, like in your phone, would it be the same thing? You have to add a power source to charge it. So would it be like, instead of silver in that picture, would it be like lithium-ion?
I don't know. Look it up and let us know. But I think with some I guess so. Some of the rechargeable ones, though, operate differently. I'm not sure. Look it up. Let us know. Get busy. Alrighty. One application you can see here is with your molten sodium chloride. You can decompose that to sodium metal and chlorine gas. So the battery will pass electricity through the molten sodium chloride. Here are your two oxidation and reduction half reactions here. And one thing I want to make clear from the get-go, because this will help you set up your equations, is that if you have something like sodium chloride, sodium ion, chloride ion, so looking at the compound, you'll then consider the ions. If they gave you a table of standard reduction potentials, something like the one provided in older AP exams, you see highlighted in blue there is the reduction of sodium ion through the gaining of an electron to generate sodium with a standard reduction potential of negative 2.71 volts. And then if you consider here, written as shown on the table, just copying here, you have chlorine gas plus 2 electrons yielding 2 chloride ions, standard reduction potential of 1.36 volts. I knew that this equation here had to be flipped because, as I said previously, look at the compound, consider the ions that you would have used to formula write that particular compound, and so all I did was flip this equation so that the ion would be a reactant. So that tells me right away that this is reduction. Reduction occurs at the cathode or the anode? Cathode. So these are all things that we talked about before break. And here's your oxidation at the anode. Just remember anox, red cat. Alrighty? So I just want to make that point clear to get it going, and you'll see where the pieces fit together within the next 10 minutes. The other thing that you would see as the reaction occurred is that the sodium metal, the cathode, would increase in mass as more and more sodium is generated. In addition, anytime you generate a gas, what will you see visually? Bubbles. And that's what you're seeing right here. So at this electrode, you're seeing bubbles being generated because chlorine gas is formed. In addition, that has a yellow-green color, so you would see that color being produced. And here you can see that the cathode is increasing in mass as the sodium is plating on that cathode. So a couple of important visual things to understand. Also, the battery signifies right away you have an electrolytic cell, not a voltaic cell. When we run our lab on Thursday, you won't need a power supply because you have galvanic or voltaic cells where the chemical reaction is thermodynamically favorable.
What are we using as a salt bridge?
In your salt bridge will be potassium nitrate, commonly used. The nitrates are really the safest. You wouldn't want to use something like silver nitrate. First of all, it's expensive, and keep in mind a lot of compounds that contain silver ion are not water soluble, so you wouldn't want to use that. But most nitrates are going to work. The ones you would probably stay away from would be silver nitrate, lead-2 nitrate, and the mercury, one or both of the mercuries, only because you could generate an unwanted precipitate. And sometimes it's not beneficial, for example, to use calcium nitrate either, because calcium sulfate is insoluble. Okay, when you are predicting electrolysis reactions, typically you're looking at 4 reactions and trying to figure out which combination is the best. 2 of the reactions will involve the splitting of water. So if you look here, you have water generating proton, oxygen gas, and electrons. This is an oxidation reaction with the 4 electrons being lost. In contrast, here's the reduction reaction where, again, water is a reactant, reacting with 2 moles of electrons to generate hydroxide ion and hydrogen gas. The net reaction then, if you add the 2 together, shows the splitting of water to generate hydrogen gas and oxygen gas, and we know that water does not naturally decompose in that fashion, so that's not going to be thermodynamically favorable. Your E cell here is going to be negative, and delta G will be positive. What evidence would one see that products are generated? What would you see visually?
Don't the 2 gases that go up in the sides of that
well, because you have gases, you would see bubbles. Would you see a color change? No. Okay. It says pure water contains so few ions that one would need to add a small amount of soluble salt. So we're going to take a look at that in just a minute. It says electrolysis of mixtures of ions. Suppose a solution contains a mixture of ions, copper 2 ion, silver ion, and zinc ion. You would start at a low voltage and then increase, and again, you have to provide a power source. In which order would the metals plate out on the cathode? Your approach here is to consider various oxidation reduction half reactions that might occur and select the redox reaction that can be accomplished at the lowest voltage. It's going to be negative. You want it as close to 0 as possible, and that will make more sense in a couple minutes. It says the more positive the E value, the more the reaction has a tendency to proceed in the direction indicated. Of the 3 reactions listed, the reduction of silver ion occurs most easily. Again, the most positive E given there in volts. So considering this approach, if you were to look at the following problem, which is in your textbook, you're going to use the same approach, and it should be very straightforward for you. It says an acidic solution contains the ions cerium 4, maybe, but it's with it's an ion though. It's a funny ion. And iron 3 ion. Using the values listed, which are here, give the order of oxidizing ability, the one most likely to be reduced, of these species, and predict which one will be reduced at the cathode of an electrolytic cell at the lowest voltage. So which one, based on those given? What has the most positive E? So it's cerium 4 ion, right? It will be reduced at the lowest voltage in an electrolytic cell. So keep that in mind. You're going to see where the pieces fit together in just a sec.
Like the negatives that are closest to 0?
You'll see. You'll see where it comes together with this piece.
Okay.
Trust me. Trust me. Haven't misled you yet. Alrighty. So now we're going to put the pieces together. It says be careful with electrolysis. So you've got sodium chloride generating sodium, metal, and chlorine gas. You're going to have 2 platinum electrodes. You're going to immerse them in the same sodium chloride solution, and you're going to connect it to a battery. Why must you connect it to a battery? Because it needs a power source. It's not thermodynamically favorable. Huh?
It's vanadate ion.
That's what it is? Vanadate? Okay.
That's
That's
what Chem Spider said.
what who said?
Chem Spider.
Wonderful. Alrighty. Are these reduction or oxidation reactions?
Reduction.
They're all reduction because the electrons are being gained. Alright? Now if you're doing sodium chloride, which ions need to be on the left side? Sodium ions. So is this equation written properly?
Yes.
What about this one? No. Now look at the water reactions. Which equation is backward? Which one?
Top end.
This blue one? That should be reversed?
Yeah.
Should I reverse this sign? You better not. Not if you want to do cathode minus anode. It says all combinations will result in a negative E cell, and therefore they're not thermodynamically favorable because the delta G will be positive. The reaction most likely to occur is the one with the least negative value of E cell because it would require the lowest applied voltage from the external source. So what I have done here, this equation I left alone. I had to flip this one so water is a reactant. So this is oxidation at the anode. Why did I flip this equation? Because chloride ion has to be a reactant. So that's clear, oxidation at the anode? Okay. You know in electrolytic cells, E cell must be negative, but you want it as close to 0 as possible. So looking at this now, it's cathode minus anode, and the combination that's going to give you a negative closest to 0 is this minus this. So E cell here is negative 2.057 volts. And we use the two equations highlighted in red. Could I calculate delta G? We said E cell here is negative 2.057 volts. And if I wanted delta G, that's equal to what? Negative N F E. How many moles of electrons would you have looking at those red equations? You have 2 in one equation, you have 4 in the other.
6.
Oh, God.
Oh, 2.
No.
4.
Why is it 4? Because you multiply that bottom red equation by 2. The least common multiple of 2 and 4 is 4, correct? Good. So you have 4 moles of electrons. Definitely can tell it's been spring break. Let's turn the brains on. And again, those of you who are banding right before spring break, you may not have watched your video yet.
Wait, what was there for band before spring?
Doesn't matter. All right. So we have 4 times 96,485 times 2.057. The negatives cancel. And delta G in 4 sig figs, I've got 7, 9, 3, 9, 0, 0 joules. Or you can do kilojoules if you wish. And that is positive, which is thermodynamically unfavorable, expected here. The rest of what's written there is very confusing, and we're not going to play with it because it's just going to blow your minds. All right. The other example that's shown is a little unusual. I'm going to skip this one for right now, and I want to look at this problem here that we're going to work together. Let's take a look. So I've printed it right here. It says, predict the electrolysis reaction when potassium bromide is electrolyzed using platinum electrodes. All right, let's take a look. Potassium bromide. Which equation or equations are written correctly? So this one and this one? Okay, so those are both reduction or oxidation? reduction. So we've got K plus an electron yields potassium, and our E is going to be negative 2.92 volts. And this is going to be reduction at the cathode. The other reduction is 2 waters plus 2 moles of electrons yielding hydroxide ion plus hydrogen gas is negative 0.828 volts.
She forgot the no.
This too?
Yeah.
Okay, thank you. What would happen to the pH as this reaction proceeded? It would increase because you're generating hydroxide ion. All right. Now, what am I going to do with this reaction? Flip it. So this is oxidation at the anode. And should I change this sign? No. We don't want to. And what about this equation? Why are we going to flip that one? Because we want what as a reactant?
And a reactant?
Oh, yeah.
We want water. Hey,
Brain is still off.
nobody in here is stupid. It's the smartest kids in the school. Alrighty. We want the combination that yields a negative but is as close to 0 as possible. What are you thinking?
828 minus the 1.07.
This minus this? Okay.
Wouldn't you just take like the smallest numbers of both the negative and the positive?
Be careful because they're not always negative. Like you can have a positive over there.
Okay.
If you had positives for the reduction ones, you would want to take the biggest number out of the oxidation ones, right? So that way you subtract from a bigger number, it's more negative.
You want it to be as close to 0 as possible.
Oh, yeah.
Why'd you add the number?
Because it was easier for my brain. It's a little math trick. I do math very differently than you do.
Wait, so you added?
Yeah, the
You added because it's the same thing. Oh, because you're just getting more
Negative
negative.
3 plus negative 5 is? Right, so I added and kept the sign.
Yeah.
Alrighty, so here's my E cell. It's negative. So that may be one thing they ask you.
Will you cleanse out if you forget that little knot thing?
Be careful with that because sometimes you're solving for that and sometimes you're not solving for that, as we talked about with the Nernst equation. So be careful with it. Whether you lose points, probably not, but just make sure you're clear on what you're solving for. So these are our two reactions. So what's our net reaction then? We'd have two, oh wait, careful. Yeah, 2 electrons here, here, so we're good there. So 2 waters plus 2 bromide ions yields 2 hydroxide ions, hydrogen gas, and bromine, which is a liquid. So for that net reaction, the pH will increase. Would you see bubbles?
Yes.
Yes. And bromine as a liquid. What color is bromine? It's like a reddish brown. That you probably wouldn't have to know. Blue gas or blue ion? Copper 2 blue.
How do you know that bromine is a liquid?
When you think about your diatomic elements, 5 are gases and 2 are not. Bromine is a liquid and iodine is a solid. Group 17 is very interesting in that you have all 3 states of matter. As you go down, you go from gases to liquids to solids, and why might that be? What controls this? What controls the state of matter? So which would have the stronger IMFs, fluorine gas or iodine solid? Definitely iodine solid. So what type of IMF are we talking about for group 17? LDFs, because they are all nonpolar covalent. So why would the LDFs in iodine be stronger than those found in fluorine gas?
Because fluorine has hydrogen bonds.
Wait, I gotta think about that.
Why would
It's a solid. So it's hard to break apart.
why would the LDFs in iodine be greater than the LDFs in fluorine? It has more electrons and therefore it's more polarizable. Yes, yes? Yes, we really reviewed over break. Yes!
Wait, Dr. Gillish. Why doesn't hydrogen bonds affect it?
Hydrogen bonding is for a highly electronegative element such as nitrogen, oxygen, or fluorine bonded. And then you can get a hydrogen bond, let's say, that way.
Gotcha.
Alrighty. Keep in mind that nonpolar covalent substances cannot participate in hydrogen bonding. Alrighty. If you do a couple of these types of problems, you will find this to be extremely simple. The other example I provided to you, we will take a quick look-see at. Unfortunately, it's a little bit odd of a problem, which is why I probably should flip my notes here. In any event, it says predict the electrolysis reaction when silver nitrate is electrolyzed using platinum electrodes. So again, silver ion, shown right here. The nitrate ion is the tricky part. And what you're looking at here is, you know that you need silver ions, so this has to be the reduction reaction at the cathode. But if you were considering the nitrate ion, if this is reduction at the cathode, this is +1 and this is 0, hence the reduction and oxidation number. Nitrogen is +5, and if you're considering oxidation now, where you lose 1 or more electrons, you would need that oxidation number to go up or down if it's oxidation. You would need it to go up because it's not being reduced, it's being oxidized. However, this is the greatest oxidation number for nitrogen, so it can't undergo oxidation, so you don't consider that reaction. And like I said, this is tricky because this is not something I think you'd ever be asked. Here's your splitting of water, reduction of water. Here's reduction of water, re-shown here. Here would be the oxidation flipped over. And now it has to be cathode minus anode, so it's something minus something to give you a negative. So why would you pick this now instead of that one?
Because the positive minus the bigger positive.
Right, so this is going to give you a number that's negative closer to 0 than this minus this. This will be a greater negative number, if you will, further to the left on the number line though. So here's your E cell. Why must delta G be positive there?
Because
It's electrolytic, or you could indicate based on delta G being equal to negative NFE, a negative times the negative E cell must give rise to a positive delta G based on delta G is equal to that equation stated, negative NFE. All right? Last thing we want to cover is quantitative electrolysis. This is very, very simple. I'm going to introduce you to a new equation, but it is one that is provided to you, so I don't foresee any problem with it. This was established by Faraday, and Faraday's constant that we've mentioned previously is 96,485 coulombs per mole of electrons. We can calculate the mass of substance generated, the moles of substance generated, or we can calculate electric current or unit of charge. There's a lot of ways to go. But if you want to look at the amount of reactant consumed or the amount of product generated during an electrolysis reaction, you need to take into account the molar mass of the substance, how much electric charge is used, and how many electrons are transferred, which is why we mentioned that previously. When you want to calculate the electric current I, which is in amps, you do Q over time. Q being the unit of charge, which is in coulombs. I like to just memorize the formula quick. Q is equal to IT. And that is provided to you in some form on your formula sheet here in the Electrochem section. It's the last equation provided, and it tells you what each variable represents as well as the units. Again, current is in amps, charge is in coulombs. Be careful, time must be in seconds. If they give it to you in minutes, you convert it to seconds. If they give it to you in hours, you still convert it to seconds. You must be in seconds or it's not going to work. The strategy to calculate moles or mass of a substance if given current and time is indicated here. You'll first calculate Q, and then through a string, a stoichiometric string, you can calculate the mass of substance. That's given to you. I'd rather just walk through how to approach this. It says what mass of gold will be deposited at the cathode in 1 hour by a current of 1.50 amps. And because they gave you gold, which is a transition element, they would need to indicate what charge the ion would have, or it won't be clear to you how many moles of electrons. So let's take a look at what's given and what's asked for. I've turned my page sideways because it is a stoic chain, and it'll be easier to read in this regard. So in this problem, we want to know the mass of gold, and that's in grams. The time is 1 hour, and so that's going to be 3,600 seconds. We'll worry about sig figs at the end. It looks like we need 3. And the current, which is I, is 1.50 amps. The only other piece of information they've given us is that gold 3 ion will gain 3 electrons to generate gold. And right here you know that you have 3 moles of electrons. So that's what's given, and now we're going to work it. Usually I do 2 steps. I know that Q is equal to I times T. I is 1.50 amps, and I'm going to multiply that by 3,600 seconds, and that's equal to 5.4 times 10 to the 3rd coulombs. If you did not have a calculator, you could work it this way. You have 3.6 times 10 to the third, and I'm going to multiply that by 3/2. Let me do it in the same order so you're not confused. 3/2, and you have 3.6 times 10 to the third. Make that 1.8. Make that 5.4 times 10 to the third, and there's your coulombs. Amps times seconds is coulombs. Now I'm going to string it. I have 5.4 times 10 to the third coulombs, and I want to get to the mass of gold. I know that 1 mole of electrons is 96,485 coulombs. Cancel, cancel. I know for every 1 mole of gold, I have 3 moles of electrons. Cancel, cancel. And from the periodic table, I know that 1 mole of gold is approximately 197 grams of gold. And this one without a calculator probably would be a little bit frustrating. The next one I think is more non-calculator friendly. And that's 3.68 grams of gold. Not so bad. You would also want to be able to go from the mass of a substance to either the current or the charge. You can work it backward. We'll take a look at that at the end. There's another problem here. Let's see if we can get this one to rip. It says, what mass of aluminum will be deposited at the cathode in 50 minutes by a current of 2 amps? So on this one, we want to know the mass of aluminum, again in grams. We've got a time of 50 minutes. If we multiply that by 60 seconds, 3,000 seconds, the current is 2 amps. And again, you're going to work this very similarly. Q is equal to IT. So we've got 2 amps times 3,000 seconds. And that's 6,000 coulombs. We have 6,000 coulombs. You're going to do the same setup, although I'm going to cheat a little bit here to show you how to do it without a calculator. Instead of 96,485, I'm going to say that's approximately 1 times 10 to the 5th coulombs. For every 1 mole of aluminum, why would I have 3 moles of electrons? Aluminum ion only has a 3+ charge, and 1 mole of aluminum is about 27 grams. So without a calculator here, you've got 3 into 27 is 9. This is 6 times 10 to the 3rd. So number of ways you can go here. You have 6 times 9 is 54, and then 10 to the 3rd over 10 to the 5th, so to the -2. So it'd be approximately 0.540 grams of aluminum, give or take, and that's probably pretty close once you plug it in. So you can do it without a calculator. Keep in mind this number should be slightly less, so this actually is a little bit more than that, but it's going to be close enough for a ballpark guess on a multiple choice situation. The last problem I want to do with you, I'll leave you with one for homework. is I want you to be able to do a comparison question. And again, this is all quantitative electrolysis. And in this comparison question, it says, which of the following solutions will yield the greatest mass? So you want to know the greatest mass. And today's a regular day. We have a few extra minutes in the period. Don't be concerned. You've got a current of 1.5 amps and a time of 30.2 minutes. And we've got copper 2 sulfate, we've got silver nitrate, and we've got gold 2 chloride. Is the Q the same for all of them? Yes, because Q is equal to IT. So the amount of coulombs does not change. You'll have some Q which is the same for all. For every 1 mole of electrons, you'll have 96,485 coulombs. For every 1 mole of substance, you will have some moles of electrons. And then for every 1 mole of substance, you'll have some gram of substance X. So for the copper 2 sulfate, how many moles of electrons will we have? 2. And copper has a molar mass of approximately 64. For the silver nitrate, how many moles of electrons? And silver ion, we said, is about 197. Silver has a molar mass of about 108, give or take. And then the gold has 2 moles. And gold is about 197. So which would have the greatest mass? How are you going to figure this out? 2 into 64 is 32. And 2 into this is going to be less than 100. Let's just say about 98 for argument's sake to keep it simple. So what's going to give you the greatest mass? The silver nitrate. And rather than writing out 3 long chains, you can do a comparison, pretty straightforward. And I tried to color code it here. I hope it worked because I went like low, middle, and then on the outsides. But it's something that can be done. The very last problem you should do for next time, and I'll reveal the answer to make sure you can do it, but essentially you're just stringing it backward. They're giving you the mass, and you want to be able to figure out the current. With your electrolytic cells, it's important that you can write the equation. It's important you can do quantitative electrolytic analysis, and that's going to finish out Electrochem. Lab next time.